Okay, so UFRCS 4, we're going to do parts 1, 2, and 5. Let's start with number 1. So the thing is that an ellipse is a contorted version of a circle, and a circle is easy to parameterize. So the circle, I could say, is just cosine t, sine t. No problem, right? All right, so the thing is this ellipse has semi-major, let's see, 4 along the x-axis and 2 along the y-axis. Okay, so we've got some ellipse kind of like this. And I claim that this is what you get when you take the circle, this unit circle, and stretch by a factor of 2 in the y direction and by a factor of 4 in the x direction. So now note, this is not an equation, so we're not going to use those stretching formulas from back then. I'm just literally going to take the x coordinates and multiply them by 4. I'm going to take the y coordinates and multiply them by 2. Right? Or said differently, if you want, here I can use, this is what we did back in with the equations. I could view this as the equation, and I could take x and divide it by 4, and I could take y and divide, replace y with y divided by 2, replace x with x divided by 4. But effectively, what that does is it takes the values of x and y, and it multiplies them by 4. So if you want, you can view this as being perfectly consistent with this approach that we took when we were doing equations back in 2.2, I guess it was. Yeah. So stretched out circle is the point. Yeah. Okay. And you can do something similar with part 3 here. Okay. So let's do number 2. This is the hard one. Well, this is one of the hard ones. So the surface of okay, hang on. We're going to rotate around the y-axis this curve. Okay, first let's draw the curve. X is y squared plus 3. X, y. So there's x equals y squared plus 3. I'm going to rotate that around the y-axis, and yikes. So hard to draw. Here's my original parabola in the xy plane. And when I rotate that around the y-axis, it makes one of these hyperboloid things. Oh, excuse me, it's not a hyperbola. That's a parabola, not a hyperbola. Excuse me. But it looks kind of sort of like a... kind of like that. Not my best art, but yeah.
Around the y-axis?
Yeah, we rotated around the y-axis here. So I claim when you take this curve and rotate around the y-axis, it's going to make something kind of like that. Just sort of going around like that. Okay, so here's what I'm going to do. This is a useful trick for parameterizing, and I think, I don't remember if there's an example in the book on this. I can't remember. But what I'm going to do is I'm going to find a way to describe just any way what I could possibly find to describe where this point is. And one way to do that is to describe, let's drop a perpendicular over here to the y-axis. And let's talk about its y-coordinate. And let's also talk about its angle. I mean, of course, there's a bunch of points that have that same y-coordinate, and I distinguish those points with the same y-coordinate by what this angle above the xy plane. And let's call that angle theta. So what I'm going to try to do is to solve for x, y, and z, all in terms of these two coordinates, y and theta. Well, good news, y is easy to solve for in terms of y and theta. It's just y. So what is x? Well, okay, so I'm going to have to know what that radius is. Let's call that radius r. That turns out to be easy. R is the same as what had been x on the original curve. So it's just y squared plus 3. That's that distance r. It's the same as that distance. And x here, I claim, is r cosine theta. Because look at this little right triangle here. And in that little right triangle, x, the value of x for that point is that distance, which is, so this is the angle theta right there. X is r times the cosine of that angle. So, what is z? Well, z is that height. Z is going to be r times the sine of that angle. And these I can rewrite as, well, remember r is this formula here. It's y squared plus 3, and then cosine theta. This is just y, and this is y squared plus 3 sine theta. So there's your parameterization. This is kind of a, so I mean, let me go back to the, let's see here, where's an example where I did something kind of like this. See, I didn't parameterize that one. Well, so if you look at this, the bicycle reflector example, I found some parameter, in this case it was theta, that I could use to describe where the reflector was. Now I had to do that by, there's a bunch of details involved, and I did it by adding, different vectors, but ultimately I described position as a function of theta. I found some parameter that I could use to describe where I was on the curve, namely how much had the wheel rotated. And then I just calculated what position was as a function of that one parameter. And that's kind of what I did in this last example, except there was 2 parameters. But nevertheless, I looked at how can I possibly describe the position of this point. Well, I need to know the y, and I need to know the theta. And then I'd solve for x, y, and z. So you can do something similar. Let me do number 5 now while we're on this strategy.
Question with the diagram. It's theta from the r to the x-axis. Theta is measured between.
Yeah, that's right. Theta is the angle between that sort of radial distance and then this. The xy plane.
XY.
Yeah, that's right. Yeah. Yeah. So let's do part 5 here. This is another tough one. Torus obtained by rotating. Okay, picture. We're going to rotate around the y-axis. The circle of radius 3, oh gosh, okay, let's see here. I've got to write this down as we go. Circle of radius 3 centered at 5, 0. So there's 5, 0. Here's a circle of radius 3. I'm going to rotate that around the y-axis. Makes a donut. Right? Torus. So, okay, now we need to draw that in the 3-dimensional context here. Let's see here. We're rotating around the y. Okay, yeah. So here's the circle that we rotate around the y-axis. And that gives us this donut, kind of like that. Now I've got to decide, well, how can I represent where I am on this donut? Well, keep in mind, this sort of, that distance there, the distance from the center of one of these cross-section circles to the z-axis, that distance is, well, not the z, to the origin. that distance is always 5. And furthermore, the distance from a point on the torus to the sort of local center of the cross section, that distance is always 3. So I mean, those are fixed. So on this picture, then, I don't need to. I mean, critically, I don't need to keep writing down 5 and 3 all the time. I just need to represent where I am on this torus in terms of what does change. And what does change is, well, I've got a couple of angles. On the one hand, I can talk about, let's look at a point, let's see here. Let's look at a point like, let's say, there. Well, there's the angle up. You know, how much did I rotate up from the XY plane? I'll call that angle, let's say, alpha. And then I've got a different angle, which is out of the XZ plane. There's this angle, beta. That makes sense? Okay. Okay. That picture isn't very good, is it? Well, gosh, I think I can just make do with that. Okay, so here's now that I have these angles chosen, so alpha and beta are what I want to parameterize in terms of, then let's look one coordinate at a time. I mean, again, I need to solve for x and y and z. And y is kind of an easy one because since I'm rotating around the y-axis, y is just that distance. And that's just going to be 3 times sine of beta. 3 sine beta, yeah.
Sine beta because you're taking the component.
Yeah, exactly, because I want to get the component that's going that way. And based on the way beta is defined, it's the angle off of the XZ plane. So that distance is 3, that radius, times the sine of that angle. Yeah. Okay, so that one was easy. Now for the x and the z, I claim that what I'm going to want to do is drop a perpendicular over here to the y-axis. And I'd like to know what is that distance. I'm going to call that capital R. That distance, capital R. And that distance kind of relates, sort of, let's see, it's this distance here, if you will. Where this angle, that angle is beta. Okay. Yay, nay? What do you think? Is that believable? I'm going to redraw a picture or something, or is everybody okay with that? You don't look happy. Not happy? Okay. So what I've got, I mean, keep in mind these two donuts are related in the following way. So I'm taking this picture in the XY plane and I'm kind of rotating it around. So this picture here got rotated up like that. So if I were to take that point, for example, and rotate it back down, right? Well, that distance still R. Right? And that's the same as this. Okay? So I claim that that capital R, I mean, I can look at this picture and see what that is. That's just going to be 5 plus 3 cosine beta. Okay? And then x and z conveniently are going to be pretty easy to write down once you have that R. X, for this point up here, X is just going to be that R times the cosine of alpha. And Z, Z, the height there, is just that R times the sine of alpha. And R is this function of beta. So yeah, the picture gets a little nasty on this one. This is a hard problem. Okay. All right. Let's see now. That was part 5, and then did we already do number? Yeah, we did. We did 2 and 3, or we did 1 and 2. 3 is the same. 3 is a lot like 1, really, and 4 is a graph parameterization. So yeah. Okay, that's a tough problem.